In this video, we are going to learn how to derive the double angle and half angle formulas. We'll start with sine of 2 theta, doubling the angle theta. The way we derive this is to take the sum formula for sine, which we know as sine of alpha cosine of beta plus cosine of alpha sine of beta. And instead of putting alpha plus beta, we'll put in sine of theta plus theta, giving us sine of theta cosine of theta plus cosine of theta sine of theta. And when we combine our like terms, we learn that sine of 2 theta is equal to 2 sine theta cosine theta. So the formula for the doubling the angle for sine is 2 sine of theta times cosine of theta. And the way we get the formula for cosine of 2 theta is actually very similar. We'll look at the sum formula for cosine, which is cosine of alpha cosine of beta minus sine of alpha sine of beta. Now, if we replace alpha and beta both with theta, so we can get theta plus theta, our formula becomes cosine of theta plus theta is equal to cosine of theta times cosine of theta minus sine of theta times sine of theta, which simplifies to cosine squared of theta minus sine squared of theta. So cosine of 2 theta is equal to cosine squared of theta minus sine squared of theta. Now, one thing I noticed in the double angle formula for cosine is that we have cosine squared and sine squared, which makes you think of the Pythagorean identities, which come from sine squared of theta plus cosine squared of theta is equal to 1. And if I wanted to figure out what cosine squared was equal to, I would just subtract sine squared theta, giving me cosine squared theta is equal to 1 minus sine squared theta. And then I could say that sine squared theta is equal to 1 minus cosine squared of theta. So to show you an alternate way to write this double angle identity, I can replace cosine squared with 1 minus sine squared. So if I take cosine of 2 theta, and instead of writing cosine squared, I write 1 minus sine squared of theta, then minus sine squared of theta, I get that cosine of 2 theta is equal to 1 minus 2 sine squared of theta, which is another way to write this identity. So there's 2 ways to write cosine of 2 theta. Another one being 1 minus 2 sine squared of theta. But if I were to replace sine, if I take cosine of 2 theta, and now I'll keep cosine squared in there, but I'll subtract a different form of sine squared known as 1 minus cosine squared of theta. Now I get that cosine of 2 theta is equal to, now we have cosine squared minus negative cosine squared, so it's a plus cosine squared. So 2 cosine squared of theta, and then minus 1. So there are 3 ways to represent the double angle formula for cosine, with the last one being 2 cosine squared theta minus 1. And now we actually get into some territory where if we were to solve for sine squared theta, we actually have a formula for sine squared theta by itself. in a different format where it gets rid of the power. Here, sine squared theta is equal to 1 minus cosine squared theta. But if I were to solve this equation, now there's not going to be a cosine squared theta anymore, but a cosine of 2 theta, which reduces the power. So we'll see here, if I were to add 2 sine squared theta onto the left and subtract 2 sine theta to the right, I could rewrite this formula as 2 sine squared of theta is equal to 1 minus cosine of 2 theta. And by divided by 2, I can say that sine squared of theta is equal to 1 minus cosine of 2 theta over 2. They often refer to these as power reducing formulas, because we went from a power of 2 to a power of 1, while this one over here just kept it at a power of 2. Now, another thing I can do is, here I have cosine squared theta. If I were to solve this one for cosine squared of theta, I can get a formula to reduce the power for cosine squared down to the cosine to the first. So again, if I add 1 to the left side, I'll get 2 cosine squared of theta is equal to 1 plus cosine of 2 theta. And by divided by 2, I can get a formula for cosine squared to be 1 plus cosine of 2 theta all over 2. And lastly, if I wanted one for tangent squared of theta, well, I know that by the quotient identity that tangent squared of theta should just be sine squared of theta over cosine squared of theta, which if I use both of these formulas, I can reduce the power by putting them over each other, meaning I have 1 minus cosine of 2 theta all over 2, which is sine squared, all over 1 plus cosine of 2 theta all over 2. And then these 2's will cancel, and I'll be left with 1 minus cosine of 2 theta over 1 plus cosine of 2 theta. So these are 3 more that aren't necessarily the double or half angle formulas, but they are very useful, because you'll see here that this angle is actually half of what's over here, and we also reduce the power. But now what I just now said, with this angle being half of what's over here, we can actually deduce half angle formulas from these power reducing formulas just by solving for the angle, for that trig function on the left. Meaning, if I were to take sine squared of theta and replace it with sine squared of alpha over 2 instead, the formula over here becomes 1 minus cosine of 2 times alpha over 2, which is just alpha by itself, all over 2. And then simply by taking a square root of both sides of this equation, I'll get sine of alpha over 2 is equal to the square root of 1 minus cosine of alpha all over 2. Now I have to be careful, because now that I take half the angle, it doesn't necessarily account for whether it's going to be positive or negative, since the square root always has to be positive. This could still be a negative value, so we'll have to keep that in mind whenever we use this formula. So this is really plus or minus the square root, depending on what quadrant half of the angle puts it in. And I could do the same for the others. So again, I could take cosine squared of theta and write that as cosine squared of alpha over 2. Which gives me 1 plus cosine of alpha instead, because 2 times alpha over 2 is just alpha. And then I could take a square root to get my formula for cosine. But again, I don't know if it's going to be positive or negative, so I have to put a plus or minus out in front. So I'll have the plus or minus the square root of 1 plus cosine of alpha all over 2 for that half-angle formula. Next up, I have tangent of alpha over 2, which again, find the exact same way by taking the theta here and replacing it with alpha over 2. Which gives me 1 minus cosine of alpha over 1 plus cosine of alpha. And when I take the square root, I get plus or minus the square roots of 1 minus cosine alpha over 1 plus cosine alpha. So those are the double angle and half angle formulas for sine, cosine, and tangent, but I did forget to get the double angle for tangent. So I want to calculate that as well, which I can calculate in a very similar fashion that I did over here by using the sum formula for tangents, which we know as tangent of alpha plus tangent of beta all over 1 minus tangent of alpha times tangent of beta, which if I replace both alpha and beta with theta, it'll be theta plus theta, which will be that 2 theta up there, giving me tangent of theta plus tangent of theta all over 1 minus tangent of theta times tangent of theta, which will simplify to 2 tangent of theta all over 1 minus tangent squared of theta. So tangent of 2 theta is equal to 2 tangent of theta all over 1 minus tangent squared of theta. So now I've completed all of my double and half angle formulas. But I'm going to explore one more expression, tangent of alpha over 2. Now while this formula does work, there actually is a formula out there that mathematicians prefer for a tangent of alpha over 2 that doesn't require this plus or minus. And it actually is calculated a very creative way. So we're going to look at 2 expressions here. And the reason why we're looking at these 2 in particular is because they can set up the identity, the quotient identity for a tangent of alpha over 2. So if I take just 1 minus cosine of alpha, which I see right here, by the way, right by sine squared of alpha over 2. If I multiply by 2 on each side of this equation, 1 minus cosine of alpha is equal to 2 times sine squared of alpha over 2. And sine of alpha, if I want to calculate sine of alpha, I can actually do this in a very creative way by think of it as the double angle formula, sine of 2 times the angle alpha over 2, which should be the same. And by using this double angle formula, I can get 2 times sine of alpha over 2 times cosine of alpha over 2. Now, you may be wondering why I did this exactly. Well, now, if I put these over each other, we can cancel out a sine and be left with sine over cosine. Especially if we put 1 minus cosine in our numerator, we'll be left with the sine up there and the cosine in the denominator. So a very creative way of writing it. So 1 minus cosine of alpha is the same as 2 sine squared of alpha over 2. All over sine of alpha, which we just calculated as 2 sine of alpha over 2 times cosine of alpha over 2. And now that I've written it this way, one of the signs in my numerator can cancel out with that sign in the denominator, and the 2's will cancel, leaving me just sine of alpha over 2 over cosine of alpha over 2. Which, by the quotient identity, that is just tangents of alpha over 2. So another way I can write this formula, instead of as the square root, I can write it as 1 minus cosine alpha over sine alpha, since I just showed that these two things are equal. So this is also equal to 1 minus cosine of alpha all over sine of alpha. And again, there's also another way I could have written this. Instead of using 1 minus cosine alpha, I could have also used 1 plus cosine alpha, which I see here, which is equal to, when I multiply by 2 times cosine squared of alpha over 2. But now I don't want to put that in my numerator because that's going to be an extra cosine. So I'll actually put that in my denominator and then put the sine of alpha in my numerator. So I'll still get tangent with sine over cosine. So it's sine of alpha over 2 is 2 sine of alpha over 2, as I showed right here, times cosine of alpha over 2. And this will be all over 1 plus cosine of alpha, which I just derived from that little formula here, as 2 cosine squared of alpha over 2. So now the cosine of alphas over 2 will cancel, as well as the 2's, but only one of them in the denominator will cancel, leaving me with, again, sine of alpha over 2 over cosine of alpha over 2, which, again, using that quotient identity, gives me tangents of alpha over 2. So again, another way, instead of using 1 minus cosine alpha over sine alpha, I can also use sine alpha over 1 plus cosine alpha. So sine of alpha over 1 plus cosine of alpha. Now we have 3 ways to write tangent of alpha over 2, just like we did for cosine of 2 theta. But the preferred one of these 3 would be the 1 minus cosine alpha over sine theta, because it leaves just one term, one factor in my denominator here, which is usually the preferred way to write any expressions, just with a single factor in the denominator. And that is how you derive the double angle and half angle formulas.